Hello student, I am Nirmala Morade from Mathematics Department, S.VK.T College, Devali Camp, Nasik. Today's topic is double integral over general region. This topic is included in chapter 4 multiple integral, which is from paper first calculus of several variables. If you remember, in last lecture we studied double integral over rectangle, its algebraic properties, as well as we studied iterate integrals and the Fubini's theorem and the related examples. Now let us recall all these first. So double integral over the rectangular region or rectangle is nothing but limit of summation of f of si yi into delta ai, I is from 1 to n, and limit is we have to take on the limit as n tends to infinity. If this limit exists, then we say that the function is integrable, and this limit is called, the value of the limit is called the double integral of the given function over the rectangle. Also we have studied the algebraic properties of the double integral in last lecture, and these properties are useful for doing the example, for solving the examples. There are two types of iterate integrals. First, we integrate the given function with respect to x first and then with respect to y. This concept is nothing but just like a partial derivative. And the another integral is, first we have to integrate with respect to y and then with respect to x. So in last lecture we studied Fubini's theorem, and that theorem gives, if the function is continuous on the given region, rectangular region R, then the double integral is same as the iterate integrals, and both iterate integrals are equal here. So it gives the double integral in terms of the iterate integrals. Now in today's lecture we will cover all these topics. So what are the topics? We will cover the double integral over the more general region. This is our first point. Second is we will consider the Fubini's theorem for more general region and the related examples. Actually the concept of double integral over rectangle, it just extend for the more general regions. So actually the logic is similar as over the rectangle. So now after watching this video, students are able to understand the concept of double integral over the more general region, how to extend the concept of double integral from rectangle to the more general region. This is our first point. Second one is students are able to find the limit of integration. Now when we have to find the double integral or triple integral, the most important part or most difficult and complicated part is how to write the limit of integration. So after watching this video, students are able to write the limit of integration for the given integration, and also able to solve the example by using the Fubini's theorem. So these are our objective. Now let us start our lecture now here. So we consider double integral or more general region. If you remember, in rectangular region, in rectangle we subdivided that rectangle into n sub-rectangles. Now draw the same, use the same thing here. So we have to given, suppose this given function f is given, it is a function of two variable. Now we integrate this over the more general region. Suppose the region is R as shown in the figure, and so now here first we have to divide this region into sub-regions by drawing vertical and horizontal lines as shown in the figure. This is our figure. Now here suppose we consider one sub-rectangle here, and in one sub-rectangle we consider one point. Suppose that point is denoted by sk, yk. And now find the area of this subrectangle. So area of this subrectangle is length equals to delta xk, breadth equals to delta yk. Multiplying this, we get the area of this subrectangle. Now denote this area as delta ak. Then we select some arbitrary point from this rectangle inside the rectangle. Suppose that point is xk, yk. Find the functional value at this point, that is we have to find f of xk, yk. Then multiply this value with the area of that rectangle, that is f of xk, yk and delta ak, this product. Do same thing for the other subrectangles and now form the sum, which is denoted by sk here. Sk equals to summation of f of sk, yk into delta ak, k is running from 1 to n. Now this sum is taken over those rectangles which are completely lies inside the our region, that is region R. So that is we have to calculate this sum over the shaded region as shown in the figure, or see the shaded region. We have to consider all the sum, all the rectangles, those who are completely inside the rectangle, and we take this sum over only that rectangles. After this, we have to find the limit of this sum as a n tends to infinity. So this limit is taken such that the linear dimension of the rectangle tends to 0 or approaches to 0. The largest linear dimension tends to 0. If this limit exists, limit of xk as n tends to infinity exists, then this limit is called as the double integral of the function f over the region R, and function is said to be integrable. So remember, if a limit of summation of f of sk, yk into delta ak as a k is from 1 to n, and the limit, we have to consider limit as n tends to infinity, that is here n approaches without any limit. If this limit exists, then function is said to be integrable, and the value of the limit is called the double integral of the given function over the given region. Now it is denoted by this symbol. So these are the notation to denote the double integral of f over the region R. So here we can write dA, or instead of that we can write dx or dA also. So this is our definition. Double integral of f of xy dA over R is same as the limit of this sum. Okay. So now while solving the integral, first we consider which types of regions are there. So according to, it is easy to evaluate the integral. So we consider there are two types of the region. So type 1 region means it is expressed as a function of, we consider a plane region here, and if we say that it is type 1, so it can be expressed as a or it is between the two continuous graph. So now see, D can be expressed, it is the set of all x, y such that A is less than equal x is less than equal b, and g1 x is less than equal y is less than equal g2 x. So this region is bounded between these two curves, g1x and g2x, both are continuous on closed interval a to b, and between the two straight lines x equals to a and x equals to b. So now see, this is one example of the region type 1. So here you can observe that region D is bounded between the two straight line x equals to a and x equals to b, and between the two continuous curve of which are the function of x. So lower curve is denoted by y equals to g1x and upper curve is y equals to g2x. So this region is said to be type 1. So this is another example of region type 1. Here again this region D is bounded between the two curves. The lower one is y equals to g1x and upper one is y equals to g2x, and between the two straight lines x equals to a and x equals to b. So now type 2 region means the region is bounded between the two continuous functions which are the functions of y. So this can be expressed in this form: D is the set type 2 region, can be expressed as D is the set of all ordered pair xy in R2 such that C is less than equal Y is less than equal D and H1x is less than equal Y is less than equal, here should be H is a function of Y and X lies between these two. H1y is less than equal, H1y is less than equal, X is less than equal, H2y. Here should be Y. There is one mistake, please correct it. So now this is a function. This is a region of type 2. So observe here, this region D is bounded between the two continuous curves which are functions of Y. The leftmost curve is x equals to h1y and the rightmost curve is x equals to h2y, and it lies between the two straight lines y equals to c and y equals to d. That is, region of type 2 is bounded between the two straight lines y equals to c, y equals to d, and another two curves x equals to h1y and x equals to h2y. Okay. So this is another example of region type 2. Here this region D is again bounded between the two horizontal straight lines y equals to c and y equals to d, and the two curves, the leftmost curve is x equals to h1y and x equals to h2y. So these are the regions of type 2. So now already in last lecture we studied what are the algebraic properties of double integral or the rectangle. Now same properties are for double integral or the general region also. So if given functions are continuous over the given region R, then this is the first algebraic property. Double integration of k f of xy can be written as k times double integral of f over the given region R. Remember here k is a constant. Second property is related to addition. Double integration of f of xy plus g of xy over the region R is same as the double integration of f over R plus double integration of f over g. Now same property for subtraction. Next properties. So as we know that if f of xy is greater than equal g of xy over R, then the integration of f is also greater than equal the integration of g over the given region R. So now next property is if f of xy is greater than equal 0, then its double integral over the region R is also greater than equal 0. And the last property, which is known as the additive property. So the double integration of f over R is same as double integration of f over R1 plus double integration of f over R2. Here the region R is the union of two non-overlapping regions R1 and R2, just like this figure. So now see here. Just a minute. Okay, see this figure. Here R is the union of two regions R1 and R2, and these two regions are non-overlapping regions. So the additive property is useful for solving the problems also. So here additive properties are same for any type of, actually algebraic properties are same for any type of the region for double integral. So now one of the most useful application of double integral, using double integral we can calculate the volume as well as the area of the given region. So now see how to find this one. So now suppose we have to given a function f of xy which is a positive over the given region R, then we can interpret the double integration of f dA over R as a volume of the region or volume of the solid which is lies between the plane region R and the surface z equals to f of xy. Again see here, we have to given f is a positive, then the double integral of f over R is same as the volume of the region which is bounded between the plane region R and the surface z equals to f of xy. Similarly, interpretation of the double integral is the area. So for that we have to given R is a closed and bounded region. Then the area of dA over R is the area of the region R. That is, if I put f equals to 1 in double integral and the region is closed and bounded, then simply double integration gives the area of that plane region. So now let us consider some examples. So this is our first example. Calculate the double integration of sin x upon x over the region R, where R is a triangle in xy plane which is bounded by y-axis, the line y equals to x and the line y is equals to 1. So when we have to calculate the double integral over any region which is a more general region other than the rectangle, so in this case first we have to find the region of the integration, that is very important. So now here in this case R is the region of the rectangle which is bounded by the 3 straight line. First is y-axis. Sorry, here one mistake is we consider the x-axis, that is we consider x equals to 0 line. Second we consider the line y equals to x, and third we consider y equals to 1. So now first line is x-axis, second line draw the line y equals to x, y equals to x is a line which is bisect the first and third quadrant, and then draw the line x equals to 1. So after drawing these 3 lines, so we will get the region of integration which is a triangle as shown in the figure. So next important, actually first since we have to draw these straight lines, these are very simple, we must find the point of intersections here. So if you look at the vertices of the triangle, so first vertices is 0 0, next vertex which is on x axis which is 1 0, and find the last vertex which is 1 1. We can easily write, or when we want to solve these lines, find the point of intersection of any 2 lines, solve them simultaneously. Suppose I want to point of intersection of the line y equals to x and line x equals to 1, I just solve simultaneously. X equals to 1, put in the equation y equals to x, so we get 1 1 is the point of intersection. Okay. So now next part is, after drawing this region, next part is we have to write the limit of integration, or we have to write the region. So as we know that we can express the region either type 1, some of the region can be written either type 1 or 2 or maybe both of them. So now here see the given region, so we have to first write limits for y. So for that we draw a vertical line which is passing through the given line, where the lower limit of the y is nothing but where that vertical line enters the region. So when we draw the vertical line in the region and check where it enters the region. So here it enters the region, that is it enters at x axis. So the lower limit for y is 0, and the upper limit of y is nothing but where that line leaves the region. So definitely it leaves the region on above straight line, that is above side of the rectangle, and that is equals to y equals to x. So the upper limit is y equals to y is x. So y lies between 0 to x. And how to write the x limit? For that we consider all the vertical straight lines. We consider all the vertical straight lines in the region. Then consider the equation of the smallest or leftmost vertical line and the rightmost vertical line. If we draw all the vertical lines in the region, so the leftmost vertical line is nothing but the y-axis and its equation is 0, and rightmost vertical line is x equals to 1. So, okay, and so the x lies between the 2 lines 0 and 1. X equals to 0 and x equals to 1. So the given region can be written as, it is a set of all ordered pair x y such that x lies between 0 and 1 and y lies between 0 to x. So we have to express this region in type 1. So okay, now next we just put up the limits. So this is our given limit, sin x upon x, this is our given function sin x upon x, integrate over the region R. So this can be written as, first we have to integrate this with respect to y and then with respect to x. We have to integrate with respect to, so it is same as sin x upon x dy. X varies from 0 to x and then we integrate this with respect to x, so from 0 to 1. So now just we integrate the given function with respect to y, and since sin x upon x is a constant, so we write outside the integration, and just 1 is remaining, integration of 1 is y, and apply the upper and lower limit. Lower limit is 0, upper limit for y is x. So now put the upper limit x minus lower limit 0, so total answer is x. So that x gets cancelled here. We just apply the upper and lower limit here. First we have to put y equals to x minus, then put in the same bracket we have to put y equals to 0, so second term definitely becomes 0. Here x gets cancelled, only sin x is remaining. Now integrate this sin x with respect to x. So integration of sin x is minus cos x, upper limit is 1, lower limit is 0. So first we have to put the upper limit, so minus cos 1 minus minus becomes plus cos 0, which is 1. So this is our answer. Okay, this is our second problem. Find the area of the region R which is bounded by the lines y equals to x and y equals to x square in the first quadrant. So now as we know that the formula for the area is double integration dA over the region R. So now here first thing is we should draw the region, which is very important. So first is the region is bounded by the line y equals to x and y equals to x square. Y equals to x is a straight line which bisects the third and fourth quadrant, and y equals to x square is a parabola, and we consider the region only in the first quadrant. So for that first we have to find the point of intersection of these two curves by solving these two equations simultaneously. So I put y equals to x in second equation in y equals to x square, so it becomes x equals to x square. Now solve this one. First we have to take x square as a common. First shift to the left side, then take x as a common, so we get here x into 1 minus x equals to 0. So either x equals to 0 or x equals to 1. These are the 2 points. Since y equals to x, so our point of intersections are, when we put x equals to 0, y also 0, and another x equals to 1, y becomes 1 here. So 0, 0 and 1, 1 are the point of intersection. Now draw both the graphs here. So this is the graph. We have to draw first the straight line y equals to x, then y equals to x square is a parabola. Their point of intersection, first point is 0, 0, that is origin, another point is 1, 1. So to integrate this we have to express the region either in type 1 or type 2. Suppose we have to express the region in type 1. So to express the region in type 1, so for that we integrate first with respect to y and then we integrate with respect to x here. So now just observe the figure. We first draw a vertical line to decide the upper and lower limit of the y. So the value of lower limit of the y is the value where the line enters the given region. So it enters the given region, so value of y is equals to x square, and the value of y where it leaves the region is y equals to x is the lower limit of, is the upper limit of the function or upper limit of the double integration. So you have just observe that vertical line, find the upper and lower limit for y. Here the lower curve is y equals to x square, upper curve is y equals to x. So the y lies between x square and x. Similarly, to decide the limits for x, we consider or we draw all vertical lines covering the whole region R. So we consider the leftmost vertical line and rightmost vertical line of the region. The leftmost vertical line is y-axis, so its equation is x equals to 0, and if we draw the rightmost vertical line is passing through the point 1, 1, so its equation is x equals to 1. So x lies between 0, 1 here. So these are the region. So here the formula for the area equals to, we first integrate with respect to y, and then for x, y is from x square to x and x is from 0 to 1 here. So now here they first solve the inner integration. So its integration equals to y, simply put the upper and lower limit here. So upper limit is x, lower limit is x square. So first we put y equals to x minus y equals to x square. So we get x minus x square, and then again integrate this with respect to x. So integration of x is x square by 2 minus integration of x square is x cube by 3, and apply the upper and lower limit again here. If you put x equals to 1 here, so we get it is half, and if you put the if you put x equals to 1, we get 1 minus 2, 1 upon 2 minus 1 by 3, and minus lower limit is 0, so second term will be 0 here. So solve this, we get the answer 1 by 6. Okay, so let us summarize today's lecture. In today's lecture we see how to find the double integral or more general region. The procedure is similar as a rectangle, and algebraic properties of the double integral or the region and the related examples. In next lectures we will discuss the Fubini's theorem, and actually it is when these integrals, when the region is expressed either type 1 or 2, and when they are equal, and the related examples. Thank you.